The discussions in part 0 have indicated that hard networks which are wired will use copper cabling. In fact, what we have realized is that the hard networks use the same analog wiring, which is the 420 milliamp loop wiring. We know then from that background that the cable has a maximum limit run of 3 kilometers, and the 3 kilometer limit here depends on the environment as well as the size of the cable that is going to run. For instance, if the cable is slightly thinner at 0.51 millimeter diameter, then it can only have shorter runs of up to 1.5 kilometers. If, on the other hand, the environment is noisy and unshielded cable is being used, then you might need to have shorter runs. Consider the following case study where a PLC in the panel box is connected to a field device which is located on the effective floor, as well as connected to an analog input in the field. And let us take, for instance, that the wiring that has been used has a resistance of 22.9 ohms per kilometer. Now, for a hard network, it's important to ensure that the loop resistance of the network is within the limit that you desire. First of all, it must be above the minimum, which is the 230 ohms. And secondly, we also need to understand the amount of voltage or the voltage range which the field device experiences, because that might be out of bounds for the correct operation of the field device. So in this case, the red box represents the big red box with the power supply represents the PLC control panel, and the smaller box at 105 meters away to represent the splice where the two wires have been joined with an equivalent resistance of 100 ohms, and then 80 meters later it connects to a field device which is represented in a form of a current source because it's a transmitter device, and then 120 meters later we have an analog input. So the analog input in this case is represented in the form of a 250 ohms resistor. Now let's look at calculating the loop resistance. So what we will notice is that if we look at the circuit right from the positive terminal of the power supply, we see that from the positive terminal of the power supply, the circuit goes through the wiring, through the 100 ohm resistor, down through the 250 ohm resistor, back, and then it goes on through the 250 ohm resistor and back to the negative terminal of the power supply, which is here. So basically, the resistance through which the circuit experiences, it's the 250 ohm resistance, the 100 ohm resistance, another 250 ohm resistance, plus the total resistance of both runs of the cable, that the cable that goes to one from the PC control panel to the analog input, as well as the cable that returns from the analog input back to the PLC control panel. So it's important that we calculate the total distance of that cable. Now we can see from the diagram that the total distance from the table is 305 meters, which is effectively 105 plus 80 plus 120. So it's plus 120. So it's 305 meters long. So it means, therefore, in one direction, the resistance of the cable is 22.9 ohms per kilometer times 0.305 kilometers long cable. This gives us 7 ohms. Now the loop resistance then becomes all of the resistance that are in the path of that cabling. So the resistances are, first of all, the analog input, the PLC control panel, plus the 100 ohm of the splice, plus the 7 ohms of the cable that goes to the field, and then 7 ohms of the cable that returns from the field, plus the 250 ohms in the field. And this gives us 614 ohms as our total loop resistance. Now, we can see, therefore, then that this circuit can be drawn to its equivalent circuit, which is shown here below. So this simplifies our circuit in the sense that we can see all of the resistances, the 100 ohm, the 7 ohm of one side of the cable, as well as the 7 ohm of the return side, the 250 ohms of the analog input in the field, and the 250 ohms of the analog input in the control panel. In this case, can we calculate then the voltage range through which the voltage transmitter experiences? In order to calculate the voltage range, then it means we have to consider two extreme situations. Because we know that the current in the loop can only change from 4 to 20 milliamps. It means if we can calculate the voltage experienced by the transmitter when the current is minimum 4 milliamps and the voltage experienced by the transmitter when the current is maximum 20 milliamps, then we would know what the voltage range is. Because otherwise, then under normal operation, the current can only be between these two values. So in the case of when it's 4 milliamps, we can use Kirchhoff's voltage law by showing that the voltage supply here, which is 24 volts, has to be equal to the amount of voltage across all of the resistances around the cable. So remember, according to Kirchhoff's law, it's V is equal to IR. In fact, this is Ohm's law. So what we can do then is, assuming that we have the minimum current, which is 4 milliamps, then we can say the voltage supplied will be equal to the voltage across all the resistance plus the voltage across the transmitter. So this equation then gives us 24 is equal to 4 milliamps times all the resistances that are experienced, so the voltage across all the resistance plus the voltage in the transmitter. So we can solve this equation to find that the voltage experienced by the transmitter when the current is 4 milliamps is actually 21.54 milliamps. To complete our analysis then, it means we have to consider the other extreme case when the current is 20 milliamps. Once again, using Kirchhoff's voltage law, that we know that the voltage supplied by our power supply will be equal to the total voltage across this loop, which means the voltage dissipated across all of these resistors plus the voltage across the voltage transmitter. So in this case, we know that our 24 volts will be equal to the current times all the resistances plus the voltage across the transmitter. In a similar fashion, then, we can see that the voltage drop in this case is going to be 11.72 milliamps. In fact, then, if we look at the manufacturer's data sheet of what voltage ranges the transmitter might need to operate, if, say, for example, typically this transmitter needs to operate at a minimum voltage of 12 volts, then we can already tell that our network might not work particularly well, especially when the current goes near the limit, which is 20 milliamps. So another similar example might be, consider a case where you have flow control of chemicals into a mixing tank using two valves. So a flow controller is connected to two valves, and it's connected using a 24 EWG wire, which has a resistance of 84.22 ohms per kilometer. And the length of the wiring, total length of the wiring, or the maximum length of the wiring, it's 450 meters long. Now, can we calculate the loop resistance in this instance? So similarly, we can see that in this instance, the diagram above can be translated into a simpler circuit diagram shown with four resistors below. So what needs to happen here is, or what actually happens is that the flow controller acts as a transmitter, which is a current source, and that current source is supplying a current into a circuit, and the circuit, by virtue of being wired using your copper cable, it will have resistance of the cabling here, and it will also have the other resistance due to the inputs of the valve here. So this will be the inputs into the valve, where the valves are going to measure how much input or how much throttling they need to tend to. So in a typical fashion, each of the valve will have a resistance of 250 ohms because of the standard of the analog loop. Now, the loop resistance then can be calculated by taking the resistance of the cable in one direction and then the other direction, which is the return path, plus the resistance of each of the valve 1 as well as valve 2. Now, each of the resistance of the valve is 250 ohms plus 250 ohms. Now, we are told in this case that the total wiring of the circuit is 250 meters long. In this case, then it means the resistance of the cable, which is R cable plus R cable, both the forward and the return path, will simply be 84.22 ohms per kilometer times 450. So therefore, it means the loop resistance will be a total sum of these three. So please do take your time to consider these simple examples as well as looking at them further in your notes. They should be easy to follow.